Okay, so I want to look at some more examples and limits looking at, I guess, a table. And we're going to let our calculator sort of do that, just to kind of give us another approach, pun intended, to looking at limits. And so I'm going to kind of, I mean, you're going to look at this page of notes here. We'll do these examples. And it's certainly up to you. Like once you get the hang of it, just you could pause the video and do them yourself and then, check your answers. But I do want to I will walk through all of them. Okay, so but I'm going to switch screens to my calculator. Okay. And so, that very first function says we're going to approach 2 for the function x squared plus 3x minus 10 over x minus 2. So I have this function actually from before, so I'm just going to adjust this here. We'll insert a plus 3x. So we'll go ahead and do the same thing, plus 3x minus 10. And again, you want to make sure you have the whole function named denominator, in the numerator, divided by x minus 2, which I think is there. Cool. Now, we want to go to the table, and we want to make sure we're looking around 2, because that's what the limit value says. So when I go to my table setup, wherever it says, just start at 2. And, I mean, 0.001 is a pretty safe increment to change by. So I go to my table. We're starting at 2. Oops, second table. There's the graph. Okay, let's try one more time. Second table. There it is. Okay, so error at 2, we knew that, but it seems that like 6.999 and error 7.001. So it looks like what should have happened, it should be 7. So even though there's an error at 2, we know that the limit value should have been 7. And that's what we write, because it's the behavior as we get close to 2. Okay, now let's go to the next example. So we'll go back to y equals. We can clear this out. And the second example says the limit as x approaches pi over 2 of 2x minus pi. So I'm going to use a left parenthesis, say 2x minus pi over 2. So pi divided, just pi. Sorry, my bad. Divided by, and then denominator, cosine of x. I guess I didn't really need that parenthesis there, cosine of x. Okay. Now, the thing is, when you're looking at calculus and dealing with trig in calculus, you want to make sure you're in radian mode, which is the default, which is good. So now let's go to our table setup. Now we want to start at pi over 2. Now, even though we're going to actually indicate pi divided by 2 is where we want to start, as soon as you hit enter, it's going to go ahead and give you a decimal truncation, or that's fine. So we're starting at pi over 2, and we're going by 0.001. Fantastic. Go to your table. And this is pretty clear, right? It's pretty clear that the value should be -2 because everywhere around it is -2. And so, with confidence, we can say that the function, the behavior near pi over 2 should have been -2. And that's what the limit value is. So I'd fill that in. Okay. So again, at any point in time, feel free to pause the video and just solve these and then go back and check them. I'm going to go through them all, so it'll take a little time. Just whatever is best for you. So the next one is the square root of x plus 2. Notice I started a parenthesis because it's x plus 2 minus 2 in the numerator divided by x minus 2 in the denominator. So parentheses x minus 2. And then go ahead and go back to your table setup. And we want to start at 2 because that's what we're approaching. And we go to our table. And let's see. Okay, so you may not notice this one right away. So if that happens, you can just go back to your table setup and again start at 2. Maybe pick a smaller value, so I can get this 0.0001 if you want. And now go to your table. And it's a little bit clearer. Like they were approaching 0.25, which is 1/4. So if you aren't really clear or don't see what that limit value is, make it a smaller increment. Okay, number 15. Another trig function. We're already in radian mode. So we say sine of x. Where's my sine function? It's been so long. There it is. Sine x. Close my parenthesis. Divide by x. And this time we are approaching it from 0. So I go back to my table setup. I want to start at 0. We can leave that nice small increment. That is fine. Go to our table. And again, because we've picked such a small increment, it's pretty clear to see that the limit value should be equal to 1, which is nice. Okay, next problem. Number 16, I think, on our notes. So big open left parenthesis here. 2 square root of x plus 1. And then minus x minus 2. Close your parenthesis. Divided by x squared. Now, I'm not sure if I need a parenthesis here or not. So when in doubt, I would say put that there. So I'm dividing by the whole x squared. Okay. And then go ahead and go to our table setup. We want to approach 0 again. Just like last time, so we're approaching 0 and have a nice little small increment. That's great. And we go to table. And it looks like, yeah, our increment is so small, it's so easy to justify and verify that, yes, that's equal to negative 1/4. Okay, our last example, number 17, I believe. So back to y equals, clear this guy out. Big parentheses here, x squared plus 3x minus 10. Close your parenthesis, divide by x minus 3. Okay, excellent. And we are approaching 3. So we go to table setup. We want to start at 3, keep our increment. That looks great. Go to the table. Oh, my goodness. Yeah, so you've probably noticed something different in this example. It might take you a while to realize that these numbers that are negative are extremely large negative values. This is negative 8 times 10 to the 5th power, negative 4 times 10 to the 5th power, negative 2.75 times 10 to the 5th power. I mean, these are really, really large negative numbers. And on the other side, this is really, really large positive numbers. And so because the left side and the right side aren't matching, one's really large, one's really small, this doesn't exist. And in fact, if you think about the behavior of this function, this is probably an asymptote, not a whole. Right, the one side is approaching really large values of infinity, the other one is really small values of infinity. And in fact, if you go back to this, I'm going to go to this screen for just a real quick second here. If you go back and try to do a direct substitution, which I didn't do, I just went right to my calculator, right? If you do a substitution into this, like try to put 2 into this function, well, okay, 2 squared is 4. 2 times 3 is 6, so 4 plus 6 is 10, 10 minus 10 is 0, over 2 minus 2 is 0. So a direct substitution led us to a 0 over 0, which I know is a whole. We were able to get the limit values equal to 7, if you remember, the answer was 7. Okay? Number 13, put pi over 2. 2 times pi over 2 is pi, minus pi is 0, cosine of pi over 2 is 0, so we get, again, 0 over 0. Remember, our limit value was negative 2. Here you put in 2. 2 plus 2 is 4. Square root of 4 is 2. 2 minus 2 is 0 over 0. So we have 0 over 0. Yet its limit value is equal to 1/4. Right? Here, putting in 0. Sine of 0 is 0. X over 0 is 0. But its limit value is equal to 1. And then our last here example, we put a 0 here. You get 2 times root 1, which is 2, minus 0, which is 2. Minus 2 is 0 over 0 squared is 0. Or our limit value when we looked at it was negative 1/4. So all of those first 5 examples had 0 over 0. And remember, 0 over 0 is a hole in the graph. It's an indeterminate form of a number. It kind of masks what's happening. And when that happens, you can find the limit because the behavior on either side of the hole is approaching the same y value. Now, our last example, when I put 3 into this, I get 0 on the bottom, but 3 squared is 9, plus 9 is 18, minus 10 is 8. I get 8 over 0. This is not 0 over 0. This is not a hole. This is indicative of a vertical asymptote. And so I just wanted to kind of show you that. Why is our calculator able to do this? Because the first 5 examples had a hole. The last example was an asymptote.